Hi, I'm Ben-Yaakov. This presentation is entitled A Surprising Variable Inductor. I'd like to thank Evgeny Smidochky for his support in the preparation of this presentation, and also to point out that the variable inductor that I'm going to present and explain in this presentation is a product of VARIMAGNO Company, Israel, and here is the contact information. Now, there are two relevant videos to this presentation: the magnetic bypass as surprising element, and also a modified magnetic reluctance equivalent circuit and implication. They give the theoretical background of this element, this variable inductor that I'm going to discuss, although I'm giving in this presentation some basics of the theory, but for a better understanding of the theoretical aspects, please watch these two videos. I'm going to print the links at the description section of the video that you are now watching. Now, the simplest way to build a variable or controlled inductor is to have, say, a toroid with a gap, and then we have a winding here for the inductor. This is the inductor. And then we have a DC winding to which we feed the DC current. And consequently, what we are doing, we are magnetizing the ferrite. I'm assuming this is the ferrite core, and pushing the BH curve toward saturation. By this, the permeability of the ferrite is going down. Permeability is the slope here. Now, without gap, we have this BH curve. Now, with the gap, we have this curve. And here we have a fairly long portion here, which is linear, so the permeability doesn't change much. We have to go all the way here, that is to feed here fairly high current in order to see a change in the permeability and therefore in the inductance. Another problem that we have here is the coupling between the AC winding here, because this is an inductor, it's going to have AC current, like in an LC, for example, converter. And then there is a coupling between this winding and this winding, and consequently we're going to have an AC voltage. And if the impedance here is low, say it's a voltage source, then you have a very high circulating current. So these are two of the many shortcomings of this very simple construction. Now, some years ago, as a matter of fact, more than 30 years ago, Dr. Dror Medini, at that time a master student at Ben-Gurion University, and myself published a paper, A Current-Controlled Variable Inductor for High-Frequency Resonant Power Circuit. And this is the structure of the proposed variable or controlled inductor. It is built around a double E core. We have here the AC winding for the inductor, and then we have two DC windings for the bias. Now, since the flux of the AC is going this way and then in this way, then when these are connected in series, so to support each other, the voltage, the AC voltage, sort of cancels out because the polarity here and here are opposite. And therefore, at the input terminal of the bias, we see theoretically zero. Practically, we see some AC voltage. So this sort of overcomes the problem of coupling because there is a cancellation of the AC voltage. So this is the main advantage of this structure. And another very important advantage of this structure is that the DC flux is going throughout the rim, which has no gap. So therefore, it's easy to magnetize it. So we are not walking against the gap as in the simple variable inductor I've shown earlier. And therefore, it's very effective in that you need minimum current in order to get into the region of saturation. Now, the intuitive explanation of the way it works is shown here. Without DC bias, we have a high permeability of this rim here. And then with DC, the permeability goes down, and therefore the inductance that you see here, this inductance here, is going down. And here is actually a measured value. This is from the original paper. And in this particular case, we see a drop between 50 or 60 microhenry to maybe 15 with a current of up to 1 amp. Effectively, you not need more than, say, 0.5 or 0.3. Now, what are the benefits of a variable inductor? Well, you can say in general that a variable inductor sort of adds an extra degree of control above duty cycle and frequency to get, you can get probably higher efficiency and improve performance. For example, in PWM converters, we can adjust the ripple by changing the inductance and then get into BCM and therefore get soft switching. And in soft switching converter, we can adjust the inductance that is providing zero voltage switching so that at low power we can also get good zero voltage switching. And in resonant converter, we can actually work at a fixed frequency because by changing the inductance, we are changing the resonant network. And what is important is the ratio between the switching frequency and the resonant network. So by changing the inductance, we can actually work at a fixed frequency. Now, fixed frequency is beneficial because we can then synchronize it to a PWM converter, say front end, or we can lock the harmonics into specific slots so they won't interfere with some signals that we might have over the spectrum. Now, since it was published, there have been many papers, actually hundreds of papers, that showed various applications of this particular design of the variable inductor. DC-DC converter, AC to DC, LED driver, resonator, and many others. In fact, if you go to IEEE Explore and put the variable inductor as the keyword, you will get hundreds of papers. And I'm talking about papers that are using this particular design rather than others, although other designs are really the minority. Most of the papers have used the design that we have published in this paper that I've just shown. Now, as I've said, one of the advantages of this design is the cancellation of the AC voltage such that at the input to the bias, you don't see a large AC component, theoretically going down to zero. However, the voltage across each of this winding could be very high, the AC voltage, because there is a coupling between the AC here of the inductor winding to this winding. Now, if you like to have a low DC bias, then you'll have to have many turns. So the turns ratio will be very high, and consequently, the voltage of each of these windings will be very high. Now, this is not very desirable because then you have problem of insulation, and the voltage can go really very high if the number of turns is high. So this is a major problem with this particular design, which makes it more bulky because you need the space for the two windings and also for the insulation. Now, here is one form of the new variable inductor that I am presenting in this video. Let me just point out that there is a patent pending on this particular design, belongs to VARIMAGNO company. Again, this could be built around a double E core. We have a gap here. This is the inductor winding. And then we have one winding for the DC on the mid core. Again, this is one particular embodiment. It could be different structures. But in here, we have it at the mid leg. And here we have a DC voltage, or it could be any other feed with a large capacitor here to show the AC. And then we have this extra leg here with no winding, and this is what I call the bypass. Again, it is discussed in this video, and if you'd like to get the theoretical foundation of this thing, please watch this video. Now, the difference between this and the previous design is that there is one winding. Now, since you have a voltage source here or a large capacitor, then the AC voltage across this winding is zero because there's a short here for AC. Despite this, as it turns out, the AC current in this winding is not very high. This is kind of counterintuitive because you look at it, it looks like a short winding on a transformer, and you'd expect to have a very high current here, coupling between here and here. Now, the secret here is this bypass, and as I'll show here in sort of a very intuitive way, this bypass is really helping to reduce the AC current in this winding, so that despite the fact that you have here a very low impedance, there is very little circulating current in this winding. Now, due to these facts, of course, it could be smaller size, and more effective, and then you don't have the problem of very high voltage across the winding. So how does it work? When we have a AC voltage here, or AC current, then we have an AC flux. And as I'll show very briefly and in an intuitive way, this flux prefers this bypass rather than going this way. Consequently, because the AC flux here is small, the AC voltage generated is small, and consequently the AC current is small. On the other hand, we have here now a DC winding, and the path here now is within the ferrite itself. There is no gap here. So this fraction here, or this portion here, can be magnetized or can be pushed towards saturation by relatively low current as we want. So we have here the same feature as in the original design, but with one winding and with low AC current. So why is it that we are not going to have a high AC current? In this video, I'm presenting a new way to model magnetic element by the magnetic reluctance equivalent circuit. And this new way helps to explain why is it that the AC current is low. Okay, so what I'm showing here, this is just the gist of it. We have here a slab of ferrite, there is a winding on it, and then there is the load. So this is like a load rather than an excitation, okay? And we are assuming some AC flux going through this ferrite. Now the classical way to model this part here by a magnetic reluctance equivalent circuit is to have a resistor which represents the reluctance, and then a voltage source, N times I, which is the MMF. So this is the classical way of modeling this part here in a magnetic reluctance equivalent circuit. What I'm showing in this video is that rather than having this voltage source, we can replace it by an inductor. Now the value of this inductor is N squared over Rs, okay? The number of turns here and the resistance. Now, since in our case, the resistance is practically just the resistance of the wire, then this resistance is going to be very small. And if N is large, as we want it, because we want a small DC bias current, then the inductance will be very high. So if I build now a magnetic reluctance equivalent circuit of the structure, then we have here the three legs, 1, 2, 3, the middle and left and right. Okay, this is the middle one with the DC, the left and the right. The right is the bypass. And here, rather than having a dependent voltage source, I've put already this inductance. The value is N squared divided by 0.1, and 0.1 is the resistance of this one. This represents the winding of the DC. So now, here we have the winding of the inductor. There is a current here. This current is causing the MMF, which generate the flux. Now the flux is flowing this way, and now it has two ways to go, to the bypass or to this mid-leg. Now this impedance now, especially at high frequency, is very high because the inductance is large and the times omega. Then therefore, most of the flux will go this way, and only a small fraction of the flux will go into here. Now the voltage generated at the DC winding depends on this flux. Here it is. And consequently, when the flux is small, the generated AC voltage is very small, and therefore the circulating current will be small. Now, in operation, the DC current comes in here as the MMF of the DC, and this DC flux is passing through these reluctances and changing the reluctances, and consequently the inductance that is seen through this AC winding, the inductor winding, the inductance will go down. I'm not showing the relationship and the realization of the reluctance, which is a function of the magnetic flux. And here are simulation results for the case of zero DC current, zero bias. What I'm showing here is the input voltage to the AC winding, that is into the inductor. In fact, we have the voltage, we have the current, and the current, of course, is lagging after the voltage. We now also see here the fluxes, and let's start with the flux of the left side, which is the side at which the AC winding is wound on. So we have here a flux of 1.8 microweber. This is in Weber. And the right side, which is a bypass, has just about the same flux. Now the middle leg, which has the DC bias, has a much, much lower flux, as expected from the theory that I've shown from the equivalent inductor, and it is some order of magnitude actually lower than the flux coming from the AC winding. So in this case, the flux of the middle leg is small, and as a result, the current developed at the DC winding, here it is small. It's only 2 milliamp. But this is for the case of DC bias 0. When we have a appreciable high DC current, which lowers the inductance quite a bit, the situation is different because the lower permeability now affects the distribution of the fluxes. So what we see here is that the flux generated by the AC winding is about 3.6 microweber peak to peak. There is a DC, of course, component which is due to the DC bias, and I'm not counting it. I'm just talking about the AC flux, so it's 3.6 microweber. And we have also on the right side 3.5 microweber, and the difference, well, it's about, all these are approximated, just eyeballing it, it's about 4 nanoweber. So it is smaller, but not that much as in the case of the high permeability that is with zero bias. Now, consequently, the current, the AC current, now is much higher. It is about 78 milliamp RMS. However, if we look at the total RMS on the winding, we have to sum up the contribution of the DC plus the contribution of the AC. And as you can see, although it is 78 milliamp as compared to the 0.3 amp, then the contribution here to the losses is small. And in fact, we have just about the same RMS as we have with the DC itself. So the penalty here is not that much. And here's the result of the simulated inductance as a function of the DC current, the bias current. We see that at 0.3 amp, this is in amps, the inductance drops from about 40 microhenry to about 6. As it turns out, and I'll show it later on, these results don't fit very well with measurement. And the reason is that in this model, we have not taken into account leakage inductances, which are sort of added to the minimum value here. So in reality, you're not getting to that low of a inductance. Finally, I'm going to show some experimental results that were obtained with an LLC converter. The converter was run at fixed frequency. And the way to do that is that we have replaced the fixed inductor, the series inductor in this LLC converter, by the variable inductor. The converter was run at closed loop, and the inductor here, the series inductor, which was a variable inductor, was changed such that the frequency was again 100 kilohertz. So all the measurements are actually done at 100 kilohertz and adjusted by the variable inductor. The converter was a demo board by Infineon, it's 600. It's a 600 watt LLC converter. And in this case, we have replaced it by the variable inductor. And again, the unit was run at closed loop, maintaining a 12 volt at the input. And the experiments were done with various input voltages and loads. And here is the performance of the experimental inductor, variable inductor. As we can see, it starts with about 40 microhenry, and then it goes down to about 16, a little bit lower than that. And again, it doesn't fit very well with the simulation. And as I explained, the reason is that the simulation did not take into account the leakage inductance, which is sort of increasing the minimum value that you can get. And here are the results. This is again for a fixed frequency of 100 kilohertz obtained by changing the inductance of the series resonant inductor. The data is for three input voltages, 350, 380, and 410 volts. And the load will change up to about 600 watt, which is the nominal value, the maximum value of this converter. Now, what we see here is also how the inductance of the variable inductor had to be changed in order to obtain a constant frequency of 100 kilohertz. Now, we see here minimum change in this case. Now, the fixed inductor of the design, of Infineon design, is about 16 microhenry. And we see that for an input voltage of 350 volts, this will maintain a frequency of about 100 kilohertz, this nominal value. However, as the voltage is increasing to 380 and 410, the frequency will change in the original design, while in this experiment, we have returned to the 100 kilohertz by changing the value of this series resonant inductor by the variable inductor. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.